be. I mean, not based on kind of what they give you. So that's what I think. But you know. All right, it's 5:30. Let's go and get started. All right, good evening, everyone. How's everyone doing today? Kind of tired? Yeah, I know. It's starting to get that time. I'm a little bit tired too. Yeah. Hopefully everyone had a good Valentine's Day yesterday too. It kind of loses its magic once you're married, but still, my wife and I, we still had a good time. Okay. All right. So the plan for today. So we're kind of right in the middle of talking about 2D finite differences. Okay. So today will be exciting. So today we'll be actually writing a code in MATLAB. Okay. So probably that's going to be in the later half of the course. So there's quite a bit of stuff we have to do before then. But I think probably for the last 30 minutes we'll be working on a code. And if you go on Canvas right now, you should see that there's actually I posted, like, I call it a starter code for today's activity. Okay. And so you'll see this kind of as a trend throughout the course. I'm not going to make you develop codes from scratch every single time. And so for a lot of the homeworks, not this past homework, obviously, but for a lot of the future homeworks, I'll be giving you starter codes that kind of help you just do a little bit of the bookkeeping first, and then have you fill in kind of the new parts there. Okay. And so hopefully we get a good chance to work on that starter code today. Okay. I think that's it for my announcements. Are there any questions I can answer before we get started for today? All right, so let's go ahead and pick up where we left off. And so we were talking about 2D diffusion with finite differences. So the equation that we're looking to solve right now is this partial differential equation. And so it looks like this. So we have partial squared phi, partial x squared plus partial squared phi, partial y squared is equal to q of x and y. Okay. So we have our two diffusion terms. And so we have second order derivatives in both the x and y direction. And then on the right-hand side, we have the source term. Okay. And just like we talked about on Monday, the big difference that we have here is that we have both x and y, okay? And so now we need to solve this on a 2D grid. Okay. And so last time on Monday, we did a lot of the, I would say, kind of building up the infrastructure of what we need to do this. And so I'm going to scroll up just to kind of review. So, you don't have to write this down again because, we went over this on Monday, but I just kind of want to refresh your memory. Okay. All right. So kind of the big point I wanted to make, or the big takeaway from Monday, is that whenever we're doing 2D problems, we need to have multiple different ways to refer to the nodes. Okay. And so we're going to be solving our equations on a grid like this. Okay. And so here's just a very simple 16 node grid. And on the left right here, you can see that we've numbered the grid simply from 1 to 16, right? So starting from the lower left-hand corner, going from left to right, we number them 1 through 16, okay? All right, and so we call this kind of the labeled 2D grid, okay? Labeled with a unique ID number. And so we need this version here because eventually what we're going to be doing is we're going to be solving a linear system of equations, right? And so a matrix set where we have one equation per node in the grid. Okay. And so for this particular example here, we would need 16 equations. And so just so that we can keep track of which equations that we're looking at and which unknowns that we're working with, we need this ID number set. Okay. So every node needs to have its own unique ID number. Okay. But what we also need to keep track of is that each node has a physical location inside the domain. Okay. And so kind of the most basic way that we can organize that is with kind of an XY coordinate notation, okay? And so I call that the AIJ labeled grid. And so, I drew the grid again, but instead of labeling them from 1 to 16, I labeled them according to their basically their X and Y coordinates. Okay? It's just a little bit strange in that the bottom left, instead of being, I think usually we're used to that being 0, 0, just because of, the way MATLAB works and the way we do the programming, I label the bottom left node 1, 1. Okay, where the first coordinate there is the x-axis, is the x coordinate, and the second one is the y coordinate. Okay, and then each time we go over 1, then we increment that I or j up by 1. Okay, and so you can see when we go from left to right, the I value is incrementing. Okay? And then we go from bottom to top, the J value is incrementing. Okay? And so the interplay between these two grids is going to be key to our algorithms. It's going to be key to how we develop the it's going to be key to how we develop these codes and get this whole thing to work. Okay. All right. And so fast forward to kind of the end of the lecture. Right. What we did at the very end of lecture on Monday was that we actually applied finite differences to this equation. Okay. And so we took each of those second order derivatives and we applied our central differencing scheme. Okay. And then after some simplification, we end up with this finite difference formula here. Okay. Okay. So now let's talk about how we actually apply this in practice. Okay. All right, so I'm going to draw the same grid as I did before. So let's draw our 16 node grid just for the sake of this example. Okay. Or remember, each node here has both its unique ID number and also its IJ coordinates. Okay. Okay. And so for this example, let's say that we're solving the Laplace equation. And so I'm going to set the right-hand side equal to 0. So we're going to have partial squared phi, partial x squared, plus partial squared phi, partial y squared. And for now, we're just going to set this equal to 0, just for the sake of simplicity. Okay, because I want to show you kind of basically how we build up these equations. All right. And so actually, let me label these as with their ID numbers just so I can refer to them in this example. Okay. So I'm going to label this exactly as I did before. We have 1 through 16. And so for this example, what I want to do is I want to apply our finite difference formula to write down the finite difference equation for a couple nodes here. Okay. And so let's do node 6 and node 10. So node 6 obviously is right here, and node 10 is right above it. All right, so let's start with node 6 actually. So let me just kind of erase this. Okay. And so we want to write out the finite difference equation for this one. Okay, so let's go ahead and scroll up just a bit here. Okay. And so when the problem asks you to write out the finite difference equations, basically it's asking you to apply an equation like this. Okay, so let me go ahead and copy this down here. I don't know if this was faster or not, but whatever. Okay. Okay, so this is the finite difference equation. And so, when we say node 6 refers to this node right here. Okay. So when we look at phi ij is always going to be the node in question, or the kind of you can almost think of it as like the main node. Okay. Okay. All right, so let's go ahead and apply that for node 6. Right? So I usually like to do this. And so for each of the equations that I write down, I use kind of this, I just write the ID number for the node along with the colon. Okay. One thing that can help too is that you can write down the I and J coordinates for this node as well. Okay. So let's look at node 6. So node 6 is kind of, right there. And so if we look at its location relative to the origin, remember the origin has ij coordinates of 1, 1. Node 6 here is going to be 2, 2, right? And so here we have I is equal to 2 and J is equal to 2. Okay. So let's go ahead and apply our finite difference equation for this. And so first we have phi I plus 1 comma J. And so that's going to be phi I is equal to 2 here. So 2 plus 1 is 3, comma 2. Okay. Plus phi I minus 1. So that's phi I or 1, comma 2. Okay. Phi I comma J plus 1. So that's going to be phi 2, comma 3. And then phi I J minus 1. So it's phi 2, comma 1. Okay. Minus 4, phi 2, comma 2. And then for this example here, since we're solving the Laplace equation, we're going to set the entire thing equal to 0. Okay. Okay. So technically, this is the equation that we're looking for, but it's not really useful right now because everything's in I comma J. Okay? So usually what we like to do is we like to take this equation and write it in terms of its nodal ID. All right, so let's look at each of the ij coordinates here and write down the ID numbers for that. So first we have phi 3, comma 2. And so we go 1, 2, 3, comma 2. And so that's going to be node 7. Okay. We have phi 1, comma 2. Okay, so we start 1, 1. 1, comma 2 is right above that. So that's going to be phi 5. Plus phi 2, comma 3. So that should be the node right above node 6. Okay, so that's going to be phi 10. Phi 2, comma 1. That should be the node right below. So that's going to be phi 2. And then minus 4 times phi 2, 2, which of course is phi 6. Any questions on how we obtained that equation right there? Okay, so let's do the same thing. Let's do for node 10. But let's do this without a visual aid. Okay, so we kind of did that example just kind of looking at the grid. So let's see if we can do this one without looking at the grid. Okay, so node 10. So node 10, we know from the previous part that node 10 has I equal to 3 and I and J, or excuse me, I is equal to 2 and J is equal to 3. Okay. And so let's bring this equation back. Remember, we had a formula from last time that helped us in computing the ID numbers. And so remember, ID was equal to J minus 1 multiplied by NX plus I. So this is the ID number for node I comma J. Right. Let's see if we can come up with a similar formula for each of the neighboring nodes, right? So we know that when we apply this finite difference equation, we need to account for all the neighboring nodes, right? So these 4 phi values here, if we look back at the previous part for node 6, right? So if we look at node 7, node 5, node 10, and node 2, These are all the neighboring nodes for node 6. Okay. And so let's see if we can come up with an equation based on this one here to compute the ID numbers for all of their neighboring nodes. Okay. Let's do right ID, left D, top ID for the top neighbor, and bottom ID for the bottom neighbor. Okay. So the reason I'm doing this is, you know, when we get to the code later, we're going to use these formulas again, except we're going to kind of implement them directly into our code. Okay. All right. So let's look at the right ID first. And so remember the right neighbor is the node which has an I+1 value, right? So let's take our ID equation above and replace I with I+1. Okay, so if we do that, we have j minus 1 multiplied by nx plus I plus 1. Okay. So let's look at left ID. So left ID is just I minus 1, right? Because it's the neighbor to the left. And so that means I minus 1. Okay. And so if we replace I with I minus 1, we have j minus 1 multiplied by nx plus I minus 1. The top neighbor is 1 above, and so 1 above means we're going to go j plus 1. Okay. And so if we replace j with j plus 1 there, we're going to have a j plus 1 minus 1, so the ones are going to cancel out, and so we have j multiplied by nx plus I. And then for the bottom neighbor, we have j minus 1, because that's going to be 1 j coordinate below. Okay. And so we're going to take j and replace it with j minus 1. And so we have j minus 1 minus 1. And so that's going to be j minus 2 multiplied by nx plus I. Okay. And so if we take these 5 equations, including the original ID number equation, and we plug in the I and j values for node 10, we should get the ID numbers for all of the neighboring nodes as well. Okay. All right, any questions on this? Okay. All right, so let's go ahead and plug in. Okay. So let's check the ID number. So we know we kind of already know the ID number is 10, but let's just go ahead and verify. Okay. So ID here is going to be j minus 1. So j minus 1 here is going to be 3 minus 1. Okay. nx is the number of nodes in the x direction. So in this particular problem, that's going to be 4. And then our I value here is 2. Okay. So we have 3 minus 1 parentheses, that's equal to 2, multiplied by 4 is 8, plus 2 is 10. Okay, so that's good. Okay. All right, so let's compute the right ID. So using this formula up here, so we have j minus 1. So j minus 1 is 3 minus 1 multiplied by 4 plus I, which is 2, plus 1 for the right neighbor. And so that's going to give us 11. All right, so let's do the left ID. So left ID is going to be very similar. So we have 3 minus 1 multiplied by 4 plus 2 minus 1. Okay. And so that's going to give us 9. Okay. Okay, then we have our equation for top ID. So top ID is just going to be j times nx plus I. And so we have 3 times 4 plus 2. And so we have 3 times 4 is 12, plus 2 is 14. We have bottom ID, so we have j minus 2, so 3 minus 2, multiplied by 4, plus 2. Okay. And so we compute that out. 3 minus 2 is 1, times 4 is 4, plus 2 is 6. Okay, so these are all the node numbers that are going to make it into the finite difference equation for node 10. Okay. Okay. And so let's go ahead and list these out. So starting with the right IDs, we have P11 plus P9 plus P14 plus P6 minus 4 times P10 is equal to 0. Right. So that's the basics of how we apply the finite difference formula. So we kind of saw 2 different ways here. So when we did node 6, we kind of just did the visual way when you can just look at the domain. And so I think that's kind of a good way when you're first building intuition. But when you're writing the code, you're going to have to kind of just trust the equations, kind of trust the algorithms. And so we're going to have to do it kind of more similar to node 10. And later on in the class today, when we actually start writing the code, you'll kind of see that process. Okay. All right. Any questions on this example here? Okay. All right. And so that's how we apply the finite difference of formula to the interior nodes. Let's talk about boundary conditions now. Okay. And so there's going to be boundary conditions in 2D finite difference. All right. And so just like our 1D case, we're going to need boundary conditions here to complete our solutions, right? Because if you look at our formula for the finite difference, in order to apply that formula, we need to have neighbors on every single side of this, right? So we need to have a left and right neighbor, we need to have a top and bottom neighbor. Okay? But if you're on the edge of the domain, you don't have a neighbor either in one direction or more than one direction. And so for the boundary nodes, because they don't have a neighbor on every side, we're going to need to apply a different scheme there. Okay? And just like in 1D, that scheme is going to be the boundary conditions. All right. And so before we move on, we have to mention a couple assumptions here. Okay. And so just for the sake of simplicity, both in kind of explaining it and kind of more so when we're coding it, we're going to assume that each side has the same boundary conditions all throughout the entire site. Okay. And so that means that for our square domain or for our rectangular domain, we're going to have a maximum of 4 different boundary conditions. Okay. So here we have our rectangular domain. Okay. And so when I say each side of the domain has the same boundary condition, that means that this entire side, the left side of the domain, is going to have 1 boundary condition. Okay. We're going to have a second boundary condition up top, third boundary condition on the right, and a 4th boundary condition down there. Okay. So this is important because, once we're in the second dimension, what you'll see is that we're going to be applying the same boundary condition to multiple nodes, right? Because if you look at a particular side, we may have multiple nodes going down that side, right? In theory, what you could do, and a lot of practical cases are like this too, you may have one boundary condition that is applied on one part of a side, and then maybe you have a different boundary condition being applied on another part. Okay. You can definitely do that, and so and that's a lot of interesting problems are modeled like that. But for now we're kind of just starting out, and so we're going to assume that each side has the same boundary condition. Okay. Okay. And so just like we did before, we're going to have 2 types of boundary conditions. And so we're going to have Dirichlet boundary conditions and Neumann boundary conditions. The Dirichlet boundary conditions, remember what those are? Dirichlet boundary conditions refer to cases where we directly specify the solution value, right? And so here phi, we're going to say is equal to phi naught. Okay. For phi naught here, this is a directly specified value. Whereas the Neumann boundary condition, this is a specification of the solution derivative. Okay. And so if you'll notice in my formulation for the Neumann boundary condition, I took the derivative with respect to n. Okay. So n there stands for the normal vector, and we'll go over that kind of once we talk about it a bit. Okay. But because we're in 2 dimensions, you have to be kind of clear about which direction the derivative is being taken. Okay. All right, so everything that we learned in 1D about how to apply these boundary conditions, we're going to apply in 2D as well. Okay. The biggest difference here is that, because the boundary conditions are being applied on an entire side of the domain, we have multiple nodes that we need to apply these boundary conditions on. That's a big difference from 1D. So if you remember when we applied boundary conditions in 1D, we only applied those on a single node. Okay? But when we apply, the boundary condition on side 1, We're going to have to do it for multiple nodes. Okay? And so practically speaking, what this means is that we're going to need a loop to apply the boundary conditions. In particular, we're going to need 4 different loops for each side. Okay. All right. And so to kind of motivate and so to, to kind of give you a bit more details about how these loops are going to be structured, let's look at the I and j coordinates for each side of the domain. Let's look at the left boundary. Let's do this consistent numbering. So I did 2 was the top boundary. Three was the right boundary. And 4 was the bottom boundary. So what's unique about these boundaries is that they're going to have they have multiple I and j values that are associated with each node on the boundary, but they're going to be constrained in a certain way. Okay? So let's look at the left boundary first. Okay? So remember, this might help too. So remember the node in the bottom left corner. This has ij coordinates of 1, 1. Okay? And if you actually look at the ij coordinates of the top right one, coordinates of the top right node are the coordinates are nx, ny. Okay, and so this kind of sets some bounds. And so for the entire domain, the values for I and j are bounded by like this. Okay, and so we have 1 is less than or equal to I, which is less than or equal to nx. Okay, and for j goes between 1 and ny. Okay. Right, so our I and j values are kind of bound between those, and that kind of covers the entire domain. Okay. All right, so let's look and see. Let's look at the left boundary and see, as we go from the bottom of the left boundary upwards. Okay. Okay, so as we traverse the left boundary, let's see how the I and j values are going to change. Okay. So let's look at the I first. So as we traverse on the left boundary, we're staying on the kind of the very left-hand side of the domain. Okay. And what we know is that on the very left-hand side of the domain, I is equal to 1 here, right? So it doesn't matter if you're on the very bottom part of the left boundary or the very top part, your I coordinate is always going to be 1. Okay. Let's go ahead and write that down. So for the left boundary, we have I is equal to 1, and this is fixed. Okay. Meanwhile, what's changing as we go from the bottom part of the left boundary to the top is the j coordinate, right? And so as we go from the bottom to the top, we have 1 less than or equal to ny, or excuse me, 1 less than or equal to j is less than or equal to ny. Okay, so let's put that in. So we have 1 less than or equal to j less than or equal to ny. Call that the free coordinate. And so what you'll notice is that for each of the boundaries, there will be one coordinate that's fixed. Either I or j is going to be fixed, and then the other coordinate is going to be free. Okay. All right, so let's look at the top boundary now. So the top boundary of boundary two is going to go from left to right, right? And so the one that's going to be free here is actually going to be the I coordinate, right? And so we have 1 less than or equal to I, less than or equal to nx. Okay, so this makes I the free coordinate. And the fixed coordinate for the top boundary is going to be j, and it's going to be fixed at a value of ny. All right, so let's do the same thing for the right boundary. So the right boundary, the fixed coordinate is I, because we're fixed to the right side of the domain, and its fixed value is going to be nx. And then the j coordinate is going to vary between 1 and ny. Okay, so that's our free coordinate. And finally, for the bottom boundary, we have 1 less than or equal to I, less than or equal to nx. Okay, so that's our free coordinate. And our fixed coordinate is j. And it's going to be fixed at j is equal to 1 because that's the very bottom of the domain. Okay. All right, any questions on this? All right, so let's implement this. And let's see how we actually kind of write the code for applying these boundary conditions. Okay. All right. So let's do an example. All right, so let's say for the problem that we're working on, we have a Dirichlet boundary condition on the left boundary. And so let's write the code in order to make this happen. Okay. All right. So first, the key word here is Dirichlet, right? So that kind of tells us kind of the manipulations or how we're going to change the left-hand side matrix and the right-hand side vector, right? Because remember, ultimately, when we apply our finite difference equations and we apply our boundary conditions, we're going to get a system like this, right? So we have a system of matrix system of equations, right? So this is the left-hand side matrix. This right here is the right-hand side vector. So when we apply our boundary conditions or when we apply our finite difference, ultimately what that's going to do is going to make changes to the left-hand side matrix and right-hand side vector. Okay, and so for Dirichlet boundary condition, it's very simple, right? So remember, if you remember from our 1D case, we basically did two things. Okay, and so the first thing that we did was that we set the diagonal term in the left-hand side matrix we set it equal to 1. And then for the right-hand side vector, for this particular row, we set the value there equal to whatever the Dirichlet boundary condition is. Okay. So let's go ahead and let's go ahead and write the code for this so you can kind of see how this is going to shake out. Okay. And so this is where we're going to bring in the information about which boundary that we're on. Okay, so we know from this example here we're on the left boundary. Okay? And so if we look at our sheet here, we know that for the left boundary, the I value is fixed at 1, whereas the J value is free to vary from 1 to ny. Okay, so let's go ahead and write a loop for that. And so since the J value is free to vary since the J value is free to vary between 1 and y, let's go ahead and write a loop on the J index. Okay. All right. And so we have 4 I, or J, excuse me. J is going to be equal to 1. And we're going to go from 1 to ny. And so this ensures basically that, we're going to visit every instance of J. Okay. And then inside this loop, we're going to perform the modifications to our left-hand side matrix. Okay. Before we do that. Okay. And so we know, right, based on what we know of what we need to do for a Dirichlet boundary condition, we're going to have a line of code that's going to set something for the left-hand side matrix. Okay. We haven't talked about the location of the left-hand side matrix, but we know we're going to set something in the left-hand side matrix equal to 1. Okay. So this line of code here refers to this. Okay. Right. And then in that same row, we're going to change the right-hand side vector value to the Dirichlet value. Okay. So, I haven't given you a Dirichlet value here. I'm just going to give it, we're just going to call it phi naught. Okay. But this line of code is basically performing this action right here. And so if you look at the MATLAB code, we're using the MATLAB assignment operator =, in order to do this. Okay. All right. So hopefully, that makes sense. And so that, even though it's in a loop right now, this is kind of the same action that we did for the 1D diffusion case. Okay. All right. The question is, what do we put inside these parentheses, right? Because whenever we make a modification to the left-hand side matrix or the right-hand side vector, we need to know kind of where inside that matrix and where inside the vector that needs to be. Okay. And so that's what's going to go inside these parentheses. And so, basically, in other words, we need to know which row in matrix we modify. So to identify the row, right now what we have is, we know for the left boundary that I is equal to 1. Okay, so remember that's fixed. Okay, so we know the I value, and we know the J is going to vary between 1 and y, and we're writing a loop to basically iterate all of that stuff. Okay, so what we do know right now, we basically already know all of the IJ coordinates. Okay. Because we know that I is fixed at 1, and J, even though J is free, we're looping over that. We're looping over all the J values. Okay. And so basically our problem kind of boils down to this. So we need to be able to take an IJ coordinate and then transform that into a unique ID number where we can use that ID number to reference the matrix. Okay. So let's use our ID number equation that we had before. Okay. So usually I like to, we'll just call it ID. I think that's fine. Okay. And so our ID equation is going to be J minus 1 multiplied by NX and it's fine to use J here because remember, we're using the J variable name in the loop. Okay. And so since we're looping over the J variable, we can use J directly in our ID number equation. Okay. Let me not do this. The semicolons look like J's. They're not supposed to be J's. Okay. Right, so we just plug right into our ID number equation here, right? And so now that we know the ID number, we can do ID, comma ID, okay? Because that's going to be the diagonal entry, right? For the left-hand side matrix. And then for the right-hand side vector, because it's a vector, we only need one, one reference there. And so that's just going to be ID. Okay. Well, we can simplify this a bit more. Because we know that I is fixed at 1, we don't have to actually put I in this equation here. We can actually just replace that with 1. Right, and so that's the basic kind of Dirichlet boundary condition loop. Okay. So this is the boundary condition for one side, and so you would have to do this for the other 3 sides as well. Okay. And then later on today, once we look at kind of the full code, you'll see how this kind of fits into the rest of the code and where it kind of appears in the whole kind of grand scheme of things. Any questions on this? Yes.
How come we're setting the left-hand side matrix equals 1?
Yeah, that is the boundary condition. Yeah, and so for this case, this is just one boundary condition. So remember, for the Dirichlet boundary condition, we're setting phi equal to phi naught, right? So this is basically the equation that we're applying in our matrix, right? And so one way that you can think about it, and so let's say that we're doing this. So let's say that this is phi 8. Okay. And so phi 8 is sitting on the boundary. What we're saying is that phi 8 is equal to phi naught. That's basically the equation we're putting into the matrix, right? But what you don't see is that there's also phi 1 plus phi 2 plus phi 3 plus ... But all these are going to be multiplied by 0 because they don't factor into that equation because it's just phi 8. And so the way that we kind of encapsulate this kind of simple equation here is we put 1 on the diagonal right here, and then on the right hand side we put the Dirichlet value. Any other questions on this code here? Okay. All right, so let's do a Neumann boundary condition, and then we'll kind of go from there. All right, so let's do a Neumann condition. Let's do a Neumann condition on the top boundary. And so the boundary condition that we want to apply is partial phi partial n is equal to, we'll say gamma. Where gamma is our Neumann value. So that can be kind of almost anything. Okay. All right. So for Neumann conditions, we have to treat them a little bit differently. Okay. And in fact, they're actually going to be a bit different than our 1D case. Because remember, in 2D, we can have derivatives in either x or y. Okay. And so, what I promised you earlier is I would tell you kind of what this n means right here. Okay. So the reason I have this derivative with respect to n, I use this n to specify the normal direction. Okay. In other words, this is basically be the direction that's perpendicular to the boundary that we're looking at. Okay. Okay. And so for the top boundary, the top boundary looks like this. Okay. The direction that's perpendicular to it is the y direction, right? And so for the top boundary, this derivative takes this form. Okay, so it's going to be a derivative in the y direction. So this is important because when we're in 2D, the derivatives kind of take kind of a little bit of a different meaning. And usually, in these kinds of contexts, a Neumann boundary condition is used to represent things like heat flux. And usually heat flux is a quantity that goes into or out of your domain. Okay? And so you want to make sure that when you're applying these boundary conditions, you apply them in a direction that's either into or out of your domain. And so you need to apply it in the perpendicular direction. Okay. Okay. All right, so that's what that n means. Let's talk about how we actually implement this in code. Because remember, whenever we have a derivative like this, we always like to replace it with the finite difference expression. Okay. And so this is going to be no different. But we want to make sure that when we apply these derivatives, we do it in kind of a consistent way, no matter if we're on the top boundary, the bottom boundary, left boundary, or right boundary. Okay? So this is the convention that I usually like to use. And so, when we have this derivative here, what I like to do is I like to do this. And so I like to take the difference between what I call the inner node. Okay, so I'll call that phi inner minus phi boundary divided by delta. Where phi boundary here, this is the boundary node that we're considering. Okay. And phi inner is the immediate neighbor to the boundary node that leads to the interior. Okay. All right. And so for the top boundary, we have our top row of nodes like this. Okay. And so if this were the top boundary right here, this would be all the boundary nodes. Okay. The inner nodes would be the next layer of nodes just right underneath it. Okay. And so the inner nodes would be these ones right here. For this top layer, this is the top boundary. These would be the inner nodes. Of course, the domain kind of continues on from there. Right? And so what this means basically is that when you're computing or when you're implementing the Neumann boundary conditions, you need to compute two sets of IDs, right? So you need to compute the ID number of the boundary node, and you need to compute the ID number of the inner neighbor as well. Okay. All right, so let's look and see what this code looks like. All right. And so remember, we're on the top boundary. And so for the top boundary, we know the I coordinate is free. Okay, so we have 4I goes from 1 to nx. Okay. And we know the j value is fixed here. The j is going to be fixed at ny. Okay. Let's compute the ID number for the boundary node first. Okay. And so we're going to use our usual equation. And so we're going to have j minus 1 multiplied by nx plus I. Okay. But since we know that j is fixed at ny, let's go ahead and replace j with ny. Okay. And so our ID for the top boundary is going to be ny minus 1 times nx plus I. Now let's compute the ID number for the inner neighbor. Okay. So remember, the inner neighbor is going to be the one that's immediately below the top boundary. Okay. So that means for the top boundary, the inner neighbors are going to have a j value that's 1 less than the boundaries. Okay. And so if the ID number for the boundaries is ny minus 1, then for the inner ID, we're going to have ny minus 2 multiplied by nx plus I. That makes sense how we computed those two ID numbers? Okay. So now that we have these two ID numbers, let's go ahead and make the modifications to the left-hand side matrix and the right-hand side vectors. Okay? And so just to remind you, the equation that we're looking at is phi inner minus phi boundary divided by delta is equal to gamma. Okay. This is our boundary condition equation. And so let's go ahead and multiply gamma by the other side. Where gamma, remember, or excuse me, delta is the grid spacing. Okay. So this is our finite difference equation, okay, for the Neumann boundary condition. And so what this tells us is that the coefficient for inner phi is going to be 1. And the coefficient for phi boundary is minus 1. All right, so let's go ahead and encapsulate that into the code. Okay, so we have left-hand side matrix. We're going to need to have 2 lines for this. We have 2 coefficients that we need to specify. let's do the coefficient for phi boundary first. Okay, and so phi boundary is going to be ID comma ID. So that's going to be -1, okay, according to our equation. And then for phi inner, okay, here's a little bit tricky part because even though it's the inner phi, we're still in the same row for this node, right? And so our first index here is going to be still ID, but the second index is going to be inner ID. Okay, and so that's going to be equal to 1. Okay. And then we make the modifications to the right-hand side vector. And so right-hand side vector at ID, that's going to be equal to gamma times delta. All right. Any questions on how we applied these? Okay, all right, and so that's how we do the boundary conditions. And for these ones we wrote the code. So once we kind of get through the starter code, I'm going to go a little bit fast through this ones, but that's basically how you do it. And so now let's kind of put it all together. And so we talked about the finite difference equations for the interior nodes. We talked about the finite difference equations for the boundaries. And so now the only thing left is just to kind of put it all together. So let's do an example where we do just that. Okay. All right, so let's consider the following domain. I should say consider the following (2D) diffusion problem. So we start with our domain. So we have our domain here just like this. Usually what you'll see is that when I draw the domain, the boundary conditions will be listed right onto the domain. Okay, so we have phi is equal to 25 down here. E is equal to 50. We have partial phi, partial n is equal to 0. And then partial phi, partial n up top is equal to 10. Okay. Let's say the length of each side of the domain is going to be 1.5. 1.5 meters. Okay. And the equation that we're looking to solve looks like the following. Say partial squared phi partial x squared plus partial squared phi partial y squared is equal to. This time I'm going to give you a source term. And so we'll say the source term is going to be equal to 3xy. Okay. And so what we want to do for this example is we're going to write the MATLAB code that solves this problem. Using finite differences. All right, any questions on just the setup for the problem? I'm about to switch over to MATLAB soon. Right. Make sure everyone gets it all written down. So, we didn't have as much time as I thought, but I did want to get through at least the first couple sections of the code, just so that you can kind of get started on the homework. So, I know a big part of the homework is the 2D problem. So, I want to make sure that you can at least get started. And then we'll probably finish up this example on Monday. Okay. Okay, so let me go ahead and switch over to the computer screen here. Let me open up MATLAB.
Is there class on Monday?
And we're going to need Chrome as well. Stupid S-Duo thing. Skip that. Oh, good question. Yes. Yeah, Monday is a holiday. Thanks for reminding me. So actually we'll pick this up next Wednesday because there's no class on Monday. So yeah, thanks for reminding me. Okay, so if you want to access the starter code here, you're going to go to the course website. You're going to click on week 4. And then you should see a code here called 2D Diffusion Finite Difference Starter. Okay, so that's the one that we want. So let me go ahead and download that. And what you'll see here, it's a little bit hard to see kind of with it all kind of with big font here, is basically this is basically going to be all the code that you need to write for the for this one. Okay, so what we're going to do, so we'll get through as much of it today as I can, and then we'll finish it up next Wednesday. Is we're going to fill in each of these different sections. Okay. Okay. So a lot of the codes in this class, the 1D diffusion problems didn't really follow this structure because those are relatively simple. But now that we're starting to write, a little bit more complex code, I like to use the following kind of structure to the code. Okay. So when you're doing your homeworks and stuff, you're definitely, of course, you're welcome to use the same structure as me. But I know that, everyone kind of has their own distinct style of coding. And so if you have a different method that you want to use, or you want to organize the code differently, that's fine with me. As long as I can still kind of read it and understand your code, that's kind of all that I really care about. Okay. All right. And so in the first section here, we have, I basically call this section define variables. Okay. And so usually in this section, what I like to do is I like to define all the important problem parameters for the problem. Okay. So you can see here, I have a few variables already defined here. And so I have nx and ny. Okay, so in this, for now, we're setting nx and ny is equal to 4. Okay, but there's a few more things that we can define here as well. Okay, all right. So other things that we can do here is we can define the lengths of the domain in each direction. Okay, and so from the problem we know that Lx is equal to 1.5, and so this is the length of the domain in the x direction. Okay, we also know Ly. In this case, is also 1.5. And so this is the length domain in the direction. Okay. All right. Other things that we can do here is we can compute the grid spacings. Okay. And so I'm going to call them dx and dy. Right, so we have our formula for the grid spacing. So our grid spacing is just going to be Lx in the x direction, Lx divided by nx minus 1. Okay, so let's go ahead and label this. So this is the grid spacing in the x direction. Okay. And dy here is Ly divided by ny minus 1. And so this is the grid spacing. Okay. So all of these kind of, I call them kind of global variables. And so basically any variable that you're going to be using throughout the code whose value is not going to be changing usually, I usually like to define them up here. Okay. And so let me go ahead and leave a subnote here. So basically any variable that you will need and not change its value, put in this section. Okay. All right. So the reason I like to do this is because usually these parameters here, they're kind of something that applies for the entire problem. And so if you want to change something, and so let's say that we want to make this grid more refined. And so instead of 4 nodes in each direction, we're going to do 40. Okay. We can kind of very easily do that from the top of the code here. So we don't have to kind of hunt through the rest of the code. Okay. So that's why I like to put a lot of these variables up top, just so, because these are things that I usually like to change. And so putting them in up top just kind of lets it be more convenient. Okay. All right. Last thing I'm going to define up here is we need to define or make variables for the left-hand side matrix and right-hand side vector. Okay. All right, so let's define left-hand side matrix. Okay. We're going to use our trusty zeros function. And so remember, the zeros function lets us create basically a matrix here with all zeros. Okay. And so the dimensions of this matrix are going to be n tot by n tot, where n tot here is just nx times ny. Okay, so that's the total number of nodes that we have. And right-hand side vector is going to be zeros of n tot, comma 1. Okay. All right. Any questions on this? Okay. All right, so let me go ahead and let's do section 2. We can actually do section 2 in 5 minutes, just because we talked about this a lot today. Okay. All right, so section 2, what we want to do in section 2 is we want to populate the left-hand side matrix with the finite difference formula for all of the interior nodes. Okay, so that was kind of the first example that we did today with node 6 and node 10, right? Remember that one? Where for the interior nodes we apply our finite difference formula directly. Okay. Okay. But the key here is that we need to apply this for all of the interior nodes. Okay, so basically for every, and so we need to apply the finite difference formula for all ij values that are not on the boundary. And so basically we're going to be looping over all of the I and j values. Okay? But to kind of make sure that we hit all of them, we're going to use a nested for loop. Right? Just going to for I. I'm just going to use I here because just kind of stay consistent with the ij notation. Okay? So I is going to go from 1 to nx. And then inside this, we're going to have j for j is equal to 1, 2, and y. Okay. Right. And so for the interior node equations, we need to do a couple of things. And so first thing we need to do, remember, when we make modifications to the left-hand side matrix and right-hand side vector, we don't do it using the ID. We don't do it using I and j. We do it using the ID numbers, right? So first thing we need to do is compute the ID numbers for all of the nodes and their neighbors. Okay. So if you remember from the first example today, we had 5 equations, right? So we had an equation for ID, we had equations for the right neighbor, the left neighbor, top neighbor, top ID, and bottom ID. Okay. So I'll do the first one for you, just so you can see what it looks like. Okay. Okay. So remember, our equation for the ID is just j minus 1 times nx plus I. Okay. And if you remember from our first example today, the equations for the left, right, top, and bottom IDs are very similar, except, we put a little twist on these as well. Okay. Okay. Next, once we have all the ID numbers, we need to specify the coefficients for all of these nodes in the left-hand side matrix. So we're going to have 5 lines here. So we have left-hand side matrix at I know it's the time, but let me just finish this up just so you can kind of get started on the homework. Okay. Right, so we're going to need to make 5 modifications. So we're going to do it at ID, comma ID, ID, comma right ID, ID, comma left ID, ID, comma top ID, and right. And then the actual modifications that we make are going to be the coefficients in that finite difference formula. Okay, and so if you remember from the finite difference formula, we have ones for all the neighboring nodes. Okay. And then for the node itself, we have a coefficient of -4. All right, and so in 5 minutes, we covered this section. I know I went through the code fairly quickly, but it's basically a direct implementation of the example that we did earlier. So I did, I know I did take my time through, all the examples that we did in class today. But what I was hoping for is that, you kind of understand the theory of kind of where those equations came from, and then implementing them in the code is kind of similar to the previous MATLAB code that we did kind of earlier this week. Okay? Except with the added complexities that now we're in kind of 2D. Okay, and so for the rest of the sections here, section 3 may be the one that you may have a little trouble with, although although the instructions for that are kind of written in detail in the notes. We will go over that together next Wednesday. And then sections 4 through 7 are just boundary condition equations. So we just did kind of a couple examples of that kind of right before we went to this. Okay. All right. Any questions on this before we wrap it up for today? Okay. All right. And so, I apologize. I was hoping that I could get through this so that you guys can do the homeworks, but, I guess, we'll have to wait till Wednesday. But I think, if you kind of take what we learned today and kind of combine it with kind of the MATLAB that we've done before, I think a lot of you should be able to kind of figure out the rest of this. So give it a try over the weekend. If not, you can always, come for help in office hours. Even though we don't have class on Monday, I do still plan on having office hours on Monday. And so if you want to drop by on Zoom, if you're working on the homework, you can do that. Okay. All right. So thank you guys for coming today. Thanks for staying a bit late. I know I went over a bit. Have a good long weekend, and I will see you guys a week from now.
I had a question when we talk about the Dirichlet boundary condition.
Yep.
Basically, the way that I understood it was that I'm having trouble understanding how you use the left and right in the matrix to make it work together.
Sure.
But I think it seemed as though so this is just the diagonals, right?
Exactly.
And since the IDs are the same, basically, every time that they meet the same, it would just apply the values only to the diagonal.
Exactly.
That's
Yep.
for this is the Dirichlet, which is not, that's the one where it's set equal to a value, not
Exactly.
based off the derivative.
No, yeah. So Dirichlet is we're just setting the solution equal to it.
But why would it be on the diagonals if those are gonna be on the edges of the?
Yeah, so this is the part that's confusing for everyone. So for the boundary, we have two things that we're working with that look very similar. So we have a 2D domain like this,
And then a matrix.
and then a matrix.
But they're not
the same. Yeah. So the matrix, so for the 2D domain, we have nodes like this, right? So 1, 2, 3, 4. Right? So in our matrix, this actually refers to like first row in the matrix, this like second row in the matrix, third row.
Right.
Yeah, so this is confusing.
Oh, and then the diagonals, right? And then because these, everything everything between the diagonals would be all this stuff,
Exactly.
right?
Yes, right.
That's why we only care about the diagonals, because that's just going there.
Exactly. This, I know this, that's why I'm going a lot slower this year because I know people kind of really, because it's two things that look very similar.
Yeah.
And people, it's very easy to get confused. And so, yeah, I'm going a bit slower this year, but it's still, I know it's still gonna be kind of a struggle to kind of look at these.
So what if we were doing like this stuff? Would it still be diagonals?
It would be, it just would be, you know, let's say this is like node 5. And I guess this would be like 9. 13. Yeah. So the diagonal is just the fact that, remember, the matrix is just a representation of the linear equations.
Right.
So all the matrix is just a bunch of linear algebraic equations
Right.
stacked on top of each other. And so for the Dirichlet boundary, you know, let's say we have phi, we'll just do 5. So for phi 5, just going off that example, it's 25. And so this is the equation that we need to slot into row plot.
Right.
So if we look at this is E1, E2. Right? So each row of the matrix, you're going to multiply this row by this
Right.
vector here. That's our equation. And so phi 5 is equal to 25. This is the same thing as doing like E1, 0 times that, plus 0
Right.
times E2, dot, dot, dot.
And they're on the diagonals.
Right. And so the diagonals are the fact that, you know, because we're looking at node 5, we're in the 5th row. And then we're also looking at phi 5 right here. So that's also the 5th column.
Right.
Yeah. So another way you can look at this is you can look at it, you can look at the columns kind of like this as well. Right. And so if you look at the 5th row, the 5th column is going to be.
Yeah.
I kind of drew it off.
I
But
kind of get you. Okay. It's the same matrix. Same. It's all one matrix.
it's all one matrix. Yeah.
Okay. I gotta think about that.
Yeah. It's tricky. I know. Yeah. And so, you know, compared to last year, we're about maybe like half a lecture behind, but I wanted to go through this slowly. And Wednesday, I'm going to go through it more slowly. I might extend it to the homework deadlines because, you know, I don't like to finish a lecture and have a homework due just 2 days later.
Okay.
And so we'll see kind of where we are next week. But yeah, this concept is always the hardest.
Isn't that, well, it's going through the for loop, so it's just changing, each time it's changing the values. It's the same matrix,
Exactly.
but it's just updating them for each.
Exactly.
Okay, yeah, that makes
Exactly.
sense. Okay, that's why. Then I didn't understand the coefficients to be 1 and -1. Why were they?
Yeah, so it's the same thing. So we have a equation here. So the coefficient from this one, because it's.
Oh, yeah,
it's
I guess
positive.
it's 1 and -1.
Exactly.
And just underneath, the inner one is just J -1.
Exactly.
Um,
For the top boundary. For the top boundary is J-1.
Yeah.
But if you're doing like a
J
normal-
-2.
Yeah.
Oh,
Oh, yeah. J in the equation would be J.
Oh, yeah. What were you saying?
But if the Dirichlet boundary were say, I mean, if the Neumann boundary were saying the bottom, the inner nodes would be J
Both.
plus 1.
A little bit.
And then if it's on the right boundary, it'd be I minus 1. And if it's left boundary.
So we didn't write this, we wrote the pseudocode, did we?
That's basically code. So that's that you can write
But
that.
we
way.
didn't do it for this one yet. We're gonna do that still?
We
Or
did,
is
we
it
did
the
that.
same? Oh,
That was the one that
no,
we
it's
did
this
that.
one, it's right here. It's
Yes.
this. Okay, okay. Got you. Okay, cool. All right, thank you.
Yeah.
Appreciate it.